I give you guys two sheets. These two sheets are to size fire pump. It's actually one sheet back, front and back. I did it. It used to be two sheets. Now it's one sheet front and back. These are really interesting. I pulled all this information, guys, from Article 695 that talks about fire pumps. When do we need a fire pump? Who decide when we have a fire pump? That's not mainly the electrical guys, the fire marshals and a bunch of architects decide when do we need a fire pump. Most of the time, Brad, we need it if the pressure in the city, the water city, is low, below a certain limit, and I don't claim to know that limit. Then you have to have a fire pump for the sprinkler system, and also on risers. If you have, I think it's 4 or 5 story building, you require a fire pump. Everybody knows what a fire pump does, guys. They take the water from the city, it pressurize it, put some pressure on it, and throw it through the sprinkler system up on the existence of fire. So if you have a fire, the sprinkler system will go off. But if you're on the 15th floor, you don't expect that. And if you want to use the city pressure, guys, the water that's coming from the city pressure water, it's not going to reach the 15th floor. So that's why you need a fire pump. Okay, just why we need a fire pump. We don't size the actual fire pump in horsepower. The mechanical guys will come and give us a size. All what we care about, Spencer, is we have a fire pump and we need to size the electrical part of this fire pump. Okay, so whenever you go, do we have a fire pump in this building? Yes, this is how we do it. Everybody's okay with this? There are two sheets. Sheet number one, depending where you are, guys, one says at the top, sizing fire pump circuit, exactly like what you're looking at. That's what you're looking at. The second one, it says sizing fire pump with a transformer. The only difference is I stuck a transformer just in case. There are two scenarios. Either you have a transformer between the fire pump and the sources, or you don't. So I'm going to do the one that you don't have a transformer first, and guess what the second one will be? If you have a transformer, because they're slightly different the sizing. What I did, guys, I pulled all the information for you. Let me just start by right here. By code, the article that talks about the fire pump, guys, 695, it will tell you, Brad, that you have to feed the fire pump from the line side of the utility. You have, look at that. This is your service disconnect means. Can you guys see that? Service disconnect means you have to go from the line side of the service and have a separate disconnect to feed the fire pump. So that's number one. Number two, if this is not reliable and upon the authority having jurisdiction, they might force you, Spencer, to have a generator and another feed that goes through a generator. Not all the time. Sometimes they force you depending on how reliable the utility is. Most of the fire pumps that I've seen, they have a generator on site. So they're feeding also from a generator. Two sources, one from the line side of the utility, the other one from the line side of the transformer, is from a generator. And then they go to an auto transfer switch, guys. From the auto transfer switch, they go down to a controller, and from the controller, they go up to the fire pump and the jockey pump. The jockey pump, anybody knows what the jockey pump is? That's the one, it keeps the pressure in the system. So right here, can I go up here? Any question, guys, about how to feed them first?
I have a question about why you can't come into the building with the feed that's going to feed the pump.
Why can't you feed it from here?
Correct.
Reliability. They want, when the firefighters walk in and there's a fire in your building, what do? The first thing they do, they shut down the power in the whole building. So they come to the service disconnect and shut it down. If this feeder is fed from right in here, what's going to happen to the fire pump? You shut down the feeder that feeds the fire pump, so you can't, the sprinkler is off. So that's why. And this disconnect, guys, the disconnect that feeds the fire pump has to be, the disconnect that feeds the fire pump has to be, where did I, let me go back here. The disconnect that feeds the fire pump has to be identified as a fire pump disconnect. And it has to be identified as fire pump disconnect so nobody can turn it off. And also it has to be fed from the line side, just in case you walk in, you shut down the power in the building and the fire pump is still energized. Okay? Brad, that makes sense? Feeding it? No? That's a code.
No, it makes sense. I'm just wondering, I was just, because if you've got a generator, if you got it hooked up to a generator and they turn the power off, the generator's just going to kick on anyway.
No, always. The generator will kick out if you lose the power completely from the utility.
Okay.
It's the only time the gen is going to come out. So there's a fire at Dunwoody. We have a fire pump, and we have a generator. The firefighters walk in, shut down the power so they can fight the fire completely. and they leave this fire pump energized, and we're running on utility to fight the fire. The sprinkler system is on. Now, if the power globally goes down, then that big generator will handle it. And by the way, that generator is your emergency generator, could be feeding other things too. Okay? Any questions guys about the fire pump layout? Why do you think we have an auto transfer switch? Just in case we lost the power from this side, we switch and we start the generator. Then you go down. If you guys look, we have two pumps. We have the fire pump and the jockey pump. The jockey pump is a pressure maintenance pump, guys. What they do to keep the pipes energized and ready to go, they have a tiny little pump that keeps the pressure. Tiny little one. Just keep the pressure in the pipe, the sprinkler system. That's what this does all the time. It runs on a pressure switch. When the pressure in the lines goes down, it comes and pressurize it, ready to go upon the existence of a fire. And then when the fire comes, the fire pump itself pump the water. So one for pressure, one to pump the water. Any question guys about why they have this jockey pump? Okay, a couple of things about the fire pump. The utility line, I added a few things, guys. Can you guys see them right here? And I'm going to read them for you because just summarizing them. Utility feed must come from the line side of the service disconnect. That's what we said there. Also, controller must be listed as fire pump controller. You can't buy any controller here. It has to say fire rated controller, not any NEMA. They're usually red. And shall be no overload protection for the fire pump. You cannot put an overcurrent protection device for the fire pump. You can't by code. No overcurrent protection device for the fire pump. They want it to fight to run until it kills itself. So these are a few, and also the feeder that feeds it, guys. See that feeder here? The feeder, if you read that feeder right in here, has to be outside the building, under the building, or encased in 2 inches of concrete. The feeder that feeds the fire pump, big deal when you design it. You can't just put a conduit right through this. You either have to encase in 2 inches of concrete, or you have to dig underground under the building and put it under the building, or you have to go above the building or outside the building and pull that feeder. That feeder that feeds the fire pump from the generator as well as from the utility. So these are the code related, all these in Article 695. Okay, the rest is how to calculate and size this stuff. I have 10 things for you guys, starting from the branch circuits here for the 2 pumps, the controller, and then into the feeder that feeds both of them, then to the auto transfer switch, into the feeders that's coming from the service and the generator, into the overcurrent protection device that protects the whole system. Everybody can see what we're doing, Mr. Bab? Okay? Can you guys see that, what the system is? And we need to size this 10 things. Everybody's okay with that? To make it easier, DJ, my friend, I listed the code references for you guys. So on the test, please bring this one. It's confusing, guys. If you don't have this one, it is confusing. So please, when you do number 1, it's fire pump branch circuit conductor. This is how you size it. And this is how the calculation that you need to do it. Okay? So let me take, for example, we're going to take this example, guys. So all these 1 through 10, it tells you what you need to size, the steps, and the NEC code reference, and the calculation. Let's go take an example. Mr. Bab, are we good? Shall we take an example? Everybody knows what we're doing? We are sizing a fire pump system. From a generator, the utility, the auto transfer switch, and in between the controller and the fire pump and the jockey pump. And I have the references for you. There's one, bud. And you have all these calculation at the bottom. Spencer, my friend, when we have a test or something, please bring this one to the test. Otherwise, it's confusing. Okay. Having said that, then that's right. Then I'm going to go ahead. I can't write anymore. Okay. Okay. Can you guys do me a favor? Next, the example that we're going to take, it's going to be a 50. Can you write right here? It's a 50 horsepower at 480 volt or 460. This is the fire pump, and the jockey pump is going to be a 5 horsepower at also 480. That's the system that we're going to design for. Okay? So everything is 480. And all what you need is just the sizes, the two sizes, everything all the way upstream. Brad, this is very typical. Usually this one is probably 6 to 10 times more bigger than that one, because one is just to maintain the pressure, the other one is to pump the water. So that's very typical to find the jockey pump, probably 1/10 or 1/6 of the horsepower of the fire pump. Very typical. Oh, sorry, bud. No problem. Okay, you look sharp.
Thanks.
Okay, can I take a snapshot of that one and go directly into the sizing? Everybody got that sheet? You guys have it in front of you? I'm just gonna go and size for the 5 and the 10 horsepower. Mr. Abab?
Yeah, yeah.
Cool. Everybody knows what we're doing, guys? Sizing that fire pump system. Okay, let's go ahead and minimize this and go to my system here. Here's my fire pump and off it goes. Okay, minimize that one here. Grab that and off it goes. Okay, let's start with number 1. Everybody knows what we're having? Example number 1. You got it? Spencer, is it clear? No? Good. Thank you, my friend. I know your brain is somewhere else now, and I know where. Example number 1. This is what you guys, I'm gonna, it's 50 horsepower at 480. I'm gonna just repeat what I've just wrote, guys. This is my fire pump, and the jockey pump is 5 horsepower at 480 volt, and we need to find all these 10 things for them. All these 10 things for them. Let's start. Number 1. Am I going too fast?
No.
Oh.
Never.
Speed up.
Have some coffee.
Okay, let's go. Number 1. Can you guys grab that sheet in the front of you? It's really, honestly, if I give you this one and this sheet, every one of you guys should be able to do it. But let's do an example, and I'll give you a homework for it, and then we'll do the second example, and then you guys will go eat. Number 1, fire pump. Fire pump conductor. Fire pump branch circuit. This is science, Chad. Branch circuit conductors. Fire pump branch circuit conductors. You guys know what I'm looking at. Here's number 1. Can you guys see it right in front of you? That's a branch circuit. If you look at the rule, we're going to be sizing it exactly like a horsepower. So you take a 50 horsepower, take this one to table 3, 4, oops, how about 5, Chad? Take it to table 4, 30.250. And I've done that, and you find under 480 volt or 460, and that will get you a 65 amps. First of all, you need to find the full load current of the pump. That's step number 1, full load current of the pump. Right? And that's right there. The code is right in the sheet, guys. It tells you to go to table 430.250. And also, Mr. View, it tells you to go to 695.6C. That's what it tells you. 695.6C is the fire pump that refers you to what I'm doing. If you don't believe me, go there and check it. But I know you guys are trustworthy, and you trust me with a lot of stuff. Okay, the second thing is to take 1.25 as a motor times 65, and if you don't believe your friend Chad, this is at 81 amps. And the third thing, my friends, is you take the 81 amps to table 310.16 under 75 degree column. How many conductors? It's a number 4. How many conductors? 3. Thank you. Why 3? Because I don't need neutral, Chad. What's the insulation? The insulation could be THHN. It could be RH. There's an insulation RHW, I think, that they use sometimes. So let's just say it's THHN for all practical reasons. THHN. Done. Here's the first number 1. See how easy Mr. Webb is? That's like any other motor, guys. For all practical reasons, this could be any other motor that we have done. any other motor. Ryan, my friend, we're doing fire pumps, and you need this sheet for me. It's a front and back, and we're doing the one that does not have a transformer. Okay. Move on. Slow down, Chad. Chanel, are you taking notes, man? I'm gonna go check.
Please, I'm waiting to rock here.
Look at you,
Right?
sneaky guy. You take notes on the computer. I thought you were watching your girlfriend.
Oh,
Keeping an eye on these.
75 degrees. Okay. Can I?
Why would you use 75 if it's under 100?
It's a motor. Remember the exception for motors? Good point. Good point. That's why you're going to be a project manager. It's just 75. What I suggest, guys, there's a lot of stuff. Just take these sheets with you, and hopefully will help you. If you go somewhere else and they tell you otherwise, Brad, please use their ideas. It's really, that's how I understand it, and I don't claim to understand. Okay, number two. Number two, Mr. Erbab. Number two is my jockey pump. I'm not going to write these guys. Branch circuit conductors. Jockey pump, branch circuits conductors.
What's a jockey pump?
It's a maintenance pump. It's a pump that maintains the pressure in the system. They call it jockey pump. It's a maintenance pump. The technical term for it is a pressure maintaining pump. Pressure maintaining pump. Okay, good point. It's a 5 horsepower, guys. 5 horsepower. What do you guys think we're going to take it? Table 4, 30.250 again, under 480 volt. And if you go there, it's a 7.6 amper. And the second, this is 1. The second thing, you guys are going to take the 1.25, multiply it by 7.6. And if you did it like I did, you'll end up with 10 amps. And the third thing, as we have done many times, you're going to take this one to table 310.16 under 75 degree column, and you're going to end up with 3 conductors. Number, you can get away with number 14, but we don't use number 14. Please, commercially, don't even think you can get away with number 14. Don't choose anything number 14. So that will be number 12, T, H, H, N. If you on the test put number 14, it's code-wise right. You don't want to use number 14 in a commercial building. Okay, done. So these are the branch circuits that's going to the 2 pumps. The main pump, the fire pump, and the other one is the maintenance, the pressure maintaining pump, or the jockey pump. Can you go to number 3? Did we do any mistakes, Brad?
No, not yet.
Oh, I see.
Please bring it.
Thank you. Thank you.
Fire pump controller. We're going to go, if you guys are going to go ahead, the fire pump controller, all what you have to do based on DeWalt 6-4 and the voltage, you're going to find the controller for the fire pump. That's easy. I can remove, Sir Bab.
Yeah, thank you.
Thank you, my friend. Number 3, fire pump controller. For the controller, guys, I have a 50 horsepower at 480, like any other volt, and take this one to DeWalt 6-4. And if I go there, this will get me a NEMA number 3. NEMA 3. Don't forget that you're looking at voltage 480. When you go to DeWalt, you're looking at 480 volt. NEMA 3. I'll get you a NEMA 3 controller for the fire pump. Okay, the second one, number 4, guys, as you expected, this will be the jockey pump controller. Controller. Jockey pump controller, 5 horsepower at 480 volt. Take this one to the same thing. D wall 6-4 under 480 volt. Don't forget the 480 volt. That will get you NEMA number 0. NEMA 0. So the contactors will be NEMA 0 and NEMA 3 contactors with no overload. Can you guys write yourself? No overload. No overload. You don't need an overload. You cannot, by code, put an overload on these. These guys, they like soldiers. They keep fighting until they succeed or they die. Those are the Roman soldiers, not the DS.
Is that NEMA 0?
No, NEMA 0, Mr. Beth. Does it look like a 0 here?
Yeah, it's okay.
There you go. Now we make it a 0.
Yeah.
Jockey pump controller. That's number 4. Any question, guys? Make sense? All this stuff is right in that sheet in front of you, so it shouldn't be a big deal.
You say NEMA 0 or NEMA 3 and their contactors.
You're talking about contactors, and they have an overload with them, unless
So
you tell me.
Is it a single pole contactor?
All these are 3. Yeah, these are 3-phase, 3-pole contactor. Yeah. NEMA phase. When you say NEMA 3, NEMA number 0, you're going to specify it's 3-phase. I don't say 3-phase because all the systems that we do. Yeah, they are single phase though. There's a that one is single phase here. This is not a NEMA. This is an IEC. NEMAs are bigger than these, but this is single phase equivalent to NEMA. That one next to it is 3-phase. So these are 3-phase contactors without an overload. Most of the time, Brad, we don't even, unless you work for a manufacturer, these are part of the listed assembly. You tell them what the horsepower and the jockey pump, and the manufacturer will give you a listed assembly for it, really. But that's how they size it. Listed assembly contactors. 2 contactors. If you open the controller, you find 2 contactors, set of contactors, one for this pump, the other one for the other pump. Number 5. Can I go to number 5? Mr. Beth?
Yeah.
Thank you. Number 5. Number 5, my friends. Number 5 is controller feeder. Controller feeder. And you guys, you can see where the number 5 in your sheet is, right? Everybody see where the number 5 is located? That's the feeder that's coming to the controller box. So it's looking at both of them together. If you guys look at the code for number 5, it says you're going to go to the table, and 695.6c is your article, and you're going to size it like a feeder that feeds 2 pumps. So what does that mean, Chad? It means you're going to take 1.25 times, look at, this is different. This is different. 65 plus 7.6. Brad, this is the only place that I know in the code where you add them up and then you multiply them by 1.25. And where is this coming from? This is coming from the fire pump code. It's coming from the article that talks about a fire pump, which is 695.6c. If you go there, that's what it tells you. Did you guys, everybody saw that we add them, then we multiply them, unlike other feeders where we take the largest, multiply by 1.25, then we add the rest. Here we add both of them. And oh, by the way, Ben, if there's other things fed from the same controller, you just add it up. We don't have anything. Most of the time, you're not going to find anything added. So that will give me 91 amps. 91 amps. And as you guys remember, 91 amps. So you take the 91 amps, where do you guys going to take it? To 310.16, soon to be 310.15 B16, under 75-degree column because they're motors, and I end up with 3 conductors because I care less about the neutral. 3 conductor each, T, H, H, N, or other installations in the area. You might end up with THHW because of the water and so forth. Don't worry about the insulation type. Or RHW is a common one, RHW. Bless you, Mr. Bill.
Thank you.
Any question, guys, about number 5? Piece of cake? Any question about number 5, Spencer? Makes sense? Even if you have a wind turbine, Spencer, you still need to deal with fire pumps. Let me go to number 6. Muhammad, my friend, you might need this one. It comes handy. Okay. Number 6, guys, talk about sizing the ATS. Everybody knows what an ATS is? Auto transfer switch. MTS, manual transfer switch. STS. Anybody knows the STS? Static transfer switch.
Stupid transfer switch.
That's one meaning. Anybody have any rock or something I can throw at him? So, static transfer switch, guys, they transfer without you noticing any blink on the system. So if I transfer a static transfer switch and you look at this light, you go to generator, no blink in this light, not a single blink. They use them with in data centers. Okay, number 5. Let's go to number. I guess we can stick another component here. Number 6, auto transfer switch. Auto transfer switch, guys. Auto transfer switch. I do the same step. I take. What did they say for auto transfer switch here for you? Is it number? Which one are you looking at? No, you're on a long sheet. Yeah. Auto transfer switch is number 6, right? Everybody's there? We're going to go 1.25. Here's what I would do. Take 1.25, times it by both of them and size it. 65, that's my rule. 7.6, get me 91 amps, Brad. And then if you take the 91 amps, just use DeWalt, guys, DeWalt. And what's the static transfer switches? Just the same 312. 312. Use these as a guide, 312. And what's your next? These, I know these are for the disconnects, but use them as a guide for the auto transfer switch as a guide. The next is what? 100 amp. So I'm looking at 100 amp auto transfer switch. 100 amp auto transfer switch to feed this system. 100 amp auto transfer switch.
We only have 2 to go over this.
Yeah. Okay, any question, guys? Any question? All right, let's go to number. We only have 7, so we're number 7. Number 7, my friends, is conductor from the service. Conductors from service. Conductor from service, I'm just going to say same. If you guys look at the rule, same as number 5. Same as number 5. And if you guys look at number 5, we came 3 conductors, number 3, T, H, N. 3 conductors, number 3, T, H, N. Same calculation. No need for repeating ourselves. And the same thing for 8, guys. 8 conductors. Everybody can see where 8 is, right? Conductors from Gen. From Mr. Gen, same as number 5. And this will be 3 conductors. This doesn't look even close to 3. 3 conductors, number 3. THHN. THHN. Or other THW. THHN. Most likely would they use RHW, I believe. A lot of RHWs in them. RHW. So 5, 6, and 5, 7, and 8 are the same. Any question, guys? Any questions? Go to 9. 9, Mr. Bab. Yeah. 9. Thank you. Muhammad. 9. 9. 9. 9, guys. Overcurrent protection device from service. From the service. Overcurrent protection device from the service. If you guys look at this is interesting. It says, let me read this one for you. Overcurrent protection device from the service. LRC is locked rotor current. First, you need to calculate the locked rotor current for all these pumps. Here's how you calculate it. You guys remember, you take the multiplier from table 430.7b times the horsepower times 1,000 divided by the voltage and the 1.73 for three-phase. And then you add the locked rotor currents, and if it's not a standard, you go up. Thank you. Then the question would be, Chad, are you kidding me? You did not give us the locked rotor current for the motor. So go back, guys, to the source, and let's put locked rotor current, the code letter. We call them the code letter. Let's use a code letter. You have the NEC code book. Let's pick a couple of code letters here. What did we say? 430.7. I thought didn't I give you guys? What did I use here? Code letter.
430.7.
Yeah, 430. Yeah, I'm just trying to see what code letter did I use here. 430.7b 11.19. So I used the M, and for the other one I used 12.5 M and 12.49. 12.49. I used M and N. I used M code letter. You need that one, guys. I used M here. I believe, then just be consistent. I use M here and N here. Code letter N. I use N for the jockey pump and M for the fire pump. Anybody has an issue with that? Okay. All right, cool. Did you guys write? Did you edit this, please? N M. All right. Now knowing this, let's go find the first thing: locked rotor current for fire pump. The locked rotor current, guys. You guys remember it's an M for the fire pump. Then M is 11.19. 11.19. Everybody knows where 11.19 came from? 430.3b. Right? Table 430.7b. You multiply this one. What's the horsepower of this baby? 50 times 1,000, because this is the formula. Divide by 1.73 times 480. And all this mess will get you, if I did mine, give you 674 amp. 674 amps. If anybody is wondering where did this multiplier came from, this came from table 430.3b and M multiplier. I'm giving you a code letter M. Okay, let's do it for the second one. So this is step 1. Step 2, locked rotor current for the jockey pump. The same thing. The jockey pump, guys, is N. So the N is 12.49 times 5 times 1,000. Divide everything by 1.73 times 480. If you did the math on this baby, you end up with 75 amps. So I found the locked rotor current in both pumps. The last step is add them up. The last step, guys, add them up. We're going to add 674 plus 75. And if you guys, if I did that right, I came up with 749. 749 amp. Check my math. And finally, you take 749 amps, take it to 240.6, and if it's not a standard, go up to, in this case, 800 amp. This is the weird stuff. They want you guys to size the overcome protection device based on the locked rotor current. So this pump will basically run until it burns itself upon the existence of a fire. It will never trip and overload, and the circuit breaker will never trip and overload. The only time the circuit breaker will trip, guys, if you have a high short circuit. Everybody knows why. We don't care about protecting the pump, because if you have a fire in your building and half of your building is burning, do you really care about burning a fire pump? Overloading a fire pump? That's going to be the least of your problem. Everybody knows why they oversize the, look at the circuit breaker is huge, because we care less about the overload. We only care about the short circuit, and this circuit breaker will run, this pump will run until it burns itself if needed, in the process of fighting the fire. Any question, guys? This is on the service side. That's why, Mr. View, if you guys look at the fire pump disconnect or fuse disconnect or circuit breaker, you're going to see that's a huge, big. Coming out of it is a smaller conductor. That's why, because they size them based on the locked rotor current. Where does it say that size it based on the locked rotor current, Brad? It says 695.4B1, and it's in the sheet that I gave you guys, 695.4B1. It will tell you size it based on the locked rotor current. Please. It didn't say please in the code, but I added that one. Yes, Mr. Brad.
Is the table 430.7B or GB? Here it says
430.7B.
It says 3 there.
That's 7. Thank you, Mr. Bell. You got me. That's 7. 430.7. Thanks. 430.7B. Thanks, Mr. Bell. And this one is also coming. This one is coming from the same table for M. For N. This is coming from the same table for N. Any question, guys? Thanks, Mr. Bell. At least one of us is awake. I know who, too. One left. Then we do a transformer after a break. Okay. Can I move, guys? Yeah. Okay. Now let's go to the feeder that's coming from the generator. Number 10, guys, as overcurrent protection device from Gen. Everybody knows where these numbers are located, so everybody knows they're located in the graphics, so it's not confusing for you guys because you know where they're located. Brad, look how weird they do them. They size them like a feeder for the generator side. For the generator size, they take the 2.5 times 65 plus 7.6, and if you guys do that one, 170 amp. If you take, this is step 1, step 2, you take 170 amp, take this one to 240.6, and that will get you 150 amp, because you have to go down. You size exactly like a feeder over current protection that feeds multiple motors. Huh? Yeah, I'm done with that one. Yeah, let's take a quick 5. Any question, guys? Any questions? Anybody curious where the 2.5 came from, Mr. Bab? The 2.5, where did that came from? Anybody's curious? It would be table 430.52. 52. This is where this table is coming from. 430.52. Any question, guys? Any question? Okay, 5 minutes.
How many hours?
That's something funny. Can I guys get you back? Can I get you? Can I have a disclaimer? Can I erase this one and change it slightly? I think we missed one step. Do you mind, guys? Just one step. I want to erase it.
Not when I write in pen.
Oh, yes.
It must be implied.
It's the answer is the same, by the way, but the steps are slightly different. Let me just do it the right way. I missed one step. So if you guys, my friends, let's just you're gonna find the answer is still the same. Okay, here's how we do it. The first step that you're gonna do, guys, is take the biggest motor, 2.5 times 65, and that will get you 162.5 amps. The second step that you're going to take, the 162.5 amps, this should be equal here instead of 2, equal. Take this one, guys, to 240.6. You remember how we did that one? And good, it becomes 170 amp, go up. What we do, guys, we take the largest overcurrent protection device and then we add the full load current to it. I want you to change this one in a second. So that's the overcurrent protection device. Step number 3, you take the 170 overcurrent protection device. Is there 170? There is no 170. No, go up. Going up. What's the next standard up? The next standard up for circuit breaker is 175. 175. Sorry, this should be 175. You go up on the largest one, 175. So,
if you're doing step 10, it says stay without.
hold on a second. I made a mistake with this step. I'm going to change that one. 175. Hold your horses. When we do the feeder, guys, the overcurrent protection device in the feeder for motors, we take the largest overcurrent protection device, and then we add the full load current to it, and then we go down. So here's what I'm doing. I'm taking 2.5 times 65 amps. That will give me 162.5 amps. Then you take the 162.5 amps to 240.6. That will get you 175 amps. Then you add the 175 amps to what was the jockey pump's full load current, 7.6. So that will get me 175 plus 7.6 equal. That will get me 183 amps. And the last step, guys, that's what you talk about, Brad. 183 amps. Take this one to table or article 430.6 and go down. This is where we go down to, what's the next standard down? 175 anyway. 175 anyway. Let me repeat myself one more time. When we have an overcurrent protection device on a feeder, you guys did that one with me. A feeder that feeds multiple motors. How do we size the overcurrent protection device for a feeder that feeds multiple motors? You take the largest overcurrent protection device in the system for multiple motors, you add the full load current to it, and then you go down. So here's what I did. I took 2.5 because it's inverse type circuit breakers, most common, times 65, give you 162.5. Take this one to 240.6, that's 175 amp if I am to size an overcurrent protection device for the pump by itself, the fire pump, then you add the 175 to the jockey pump full load current, get this number, then you take it to 240.6 and you go down. You go down to 175. So your answer should be 175. Could you please modify the stuff, the sheet that I gave you guys to reflect this? It says 2.5 times full load current for the fire pump. That's okay, but then go find the full load current though. Go find the full load current, then you add. Then you add. Maybe I'll modify. Okay? Yeah, then you find the I'm serious, the overcurrent protection device. After you multiply, you find the overcurrent protection device for the fire pump. Then you add the jockey pump full load current. And then you go back again to the 240.6 to find the standard overcurrent protection device. And you go down if it's not standard. So I just want to highlight the down and the up. We went up on the branch circuit, down on the feeder. You guys remember that? When we did motors, we went up on the branch circuits, down on the feeders. The good news is, right, please modify the sheet that I gave you guys and bring it with you. Okay, let's go do the same thing with the transformers in between. The same thing with the transformer in between now. We're going to have a different, to spice it up, guys, we're going to have a different... Okay. Before I leave, guess what Chad is going to do to you guys? Homework. Here's what your homework is. Homework. Oops. That's right, so they don't laugh at me. Okay, that's not right. We'll get you right here.
Homework number 9.
Number 9, thank you, Mr. Beb. You're the best. You have 2.6 roughly. Homework number 9. Homework number 9, guys. Here's what I want you to do. This is 100 horsepower. This baby is 10 horsepower. The code letter for this one is B. For this one is A. That's a code letter. And the voltage for the whole system is 208 volt. It's also 3-phase as usual. And these are code letters. Okay, so here's the homework. It's a 208 system. The code letters for the two of them is AB, a 10 horsepower jockey pump and a fire pump of 100 horsepower. And do the same steps. Homework 9, cool. Mr. Bab, thank you for reminding me. So we don't lose it. Okay, let's go to the transformer. So flip the sheet that I give you guys. The second side has a transformer in it with 13 steps. I bet you probably out of the 13, 10 of them are the same. The only thing is there's 3 or 4 steps are slightly different. And we're going to go do them. Okay, let me close this. Oh, I'll have it here. There you go, Brian. By the way, that's probably the last code-related calc that we're going to be doing. Okay, let's go back to the second example. Here's the second one, my friends. Oh, don't close on me, please. Don't. All right. Let's go open it. Not a big deal. We can open it one more time. Transformer. Window crashed on me. Okay. Here's what we have, guys. Exactly the same. The only difference is I stuck a transformer right between the auto transfer switch and the controller. Could happen. Transformer between the two. That could easily happen, right? Could easily happen. And here's the example that we're going to be doing, guys. Excuse me. The transformer on this side is 480 volt. On this side, on the primary, 208 on the secondary, of course, 3-phase. And the code letter for this baby is E, and F for this. The horsepower is 7.5 horsepower for that baby, 150 horsepower for the second boy or girl. 150. Okay? The same system except we stuck a transformer, guys. We stuck a transformer. We stuck a transformer.
So now are we sizing the transformer now?
Yeah, we're gonna size the whole thing. We're gonna size 13 things.
What voltage are the pumps? Are they?
They're tied to the 208, so all of them are gonna be 208, right? Everybody can see, guys, this side of a transformer is 208, then everything is gonna be 208. This side of a transformer is 480, so everything at the top is gonna be 480. Everybody can see that? When you have a transformer, whatever tied to the primary have to take that voltage, whatever tied to the secondary has to take the secondary voltage. Okay, everybody's okay with this? 480 to 8 transformer feeding fire pump and jockey pump, 7.5 horsepower, 150 horsepower. The fire pump, the code letter is F for the jockey pump and E for the fire pump. Pull them out of the head. Let's go size these. You guys have the sheet in front of you. The sheet in front of you, buddies. It will tell you the steps. There is a few things I might have to change on you. Sorry, buds, but you'll be okay with Chad. So actually no, it will be okay. All right. Any question before we go on? Transformer feeding a fire pump through a system. The same way, Brad, we have a feeder from the line side and a generator feeder. No, nothing changed. The same requirement, except we stuck a transformer in between. Any question, Camille, my friend? Okay, can I close that one, Mr. Beb?
Yeah.
Thank you, my friend. Let's go directly into recording here. Directly into our so here's our example, and we're going to go to the first thing, Mr. Ibab. The first thing we need to is the fire pump conductors. I'm going to call them fire. You guys have it written in front of you. Fire pump branch circuit. Fire pump branch circuits. You take the 150 horsepower. Don't forget that you need to take it to table 4. 30.250 under 208 volt system, and I came up with 396 amps. Brad, did you come up with something different? Thank you. And then you take the 1.25 and you multiply it to 396, and guess what you get? 495 amps. Right? Anybody disagree? DJ, do you disagree? Do you dare to disagree? That's a challenge. And then you take the 495 amps. Did I parallel? I did not parallel here. I just did not parallel. You can. I don't want to parallel. I did not. You guys can parallel. Table 3, 10.16 under 75 degree column. 75 degree column. And I found myself a 900 kCm. 900 kCm. I found myself 3 conductors, 900 kCm RHW. RHW insulation. I'm going to use RHW commonly used. RHW. RHW. RHW installation. Any question, Mr. Bab? Do you disagree with me? Thank you. Jockey pump, what do you guys expect the jockey pump would be? Same. Except the voltage is different. I put the voltage different just to get some exercise. I mean, the example that we did was 480. This one is 280, right? Yeah. That's a piece of cake.
RHW, she's using for what?
RHW is commonly used, guys, with fire pumps. It's an installation, like THHN, THHW. RHW is an installation. Okay. Number two. Number two is the jockey pump branch circuit. We take the jockey pump branch circuit, guys. What was the jockey pump? 10 horsepower, did we say? 7.5. 7.5 horsepower. Take it to 430.250 under 208. I came up with 24.2 amps. Anybody come up with something different before we continue? 1.24, 1.25 continuous load, right? Times 24.2, and that will get me a healthy 30 amps, give or take, and a 30 ampere. If you take the 30 ampere to 310.16 cable, 75-degree column, this will get you three conductors, number 10 R AWG, AWG, RHW. RHW. Any question, guys? Any question? Piece of cake. Piece of cake. Piece of cake. Eat it, Chad, if it's cake. Can I move to 3, Mr. Bab?
Yes.
Does it make sense? Ben?
Yeah.
We're gonna rock today. Two. Go to 3. Thank you. Number 3. Number 3, my friends. You guys can continue if you are ahead of me. Number 3 is fire pump controller. Fire pump controller. You take the 150 horsepower at 208 volt, and if you go to D Walt 6-4, 6-4, guys,
Yep.
and that will get you NEMA number 6. Anybody came up with something different?
Nope.
NEMA 6. Number 4, the same thing, guys. The jockey pump controller, aka contactor size without overload. And if you take the 7.5 horsepower at 208, and everybody knows that we're 3-phase. I hope nobody will say, Chad, is it 3-phase, single phase? Everything we're doing is 3-phase now. And if you take it to D Walt 6-4, you get yourself a NEMA 1. NEMA 1. NEMA number 1. Anybody? Any? That's piece of cake. Would that be, guys, too hard if you don't have this sheet? Would that be complicated without this sheet? No? Puts things together.
Yeah, it's organized you what? When you have written
Yeah, sheet like this will help.
it helps you a lot.
Yeah. I keep working on these sheets. My assistant DJ in the summer is going to work on a lot of stuff for me. for free, volunteer, non-profit organization. I am homeless now. I don't have here at this moment.
They
Yeah,
took the odor
the lady kicked you out for watching computer.
For sleeping with the code.
Man,
as long as it's the code.
Oh, Holly, your horse is now here. For a record here. Don't give me trouble. Number 5. Controller feeder. Controller feeder. The same way, guys, we just did that one. Controller feeder is 1.25 times 396 plus 24.2. I can't emphasize, this is the only place in the code that I know of where you add them and then you multiply them by 1.25. You guys remember? And that will get me 525 amps. Now I don't know about you, Brad, but 525 amps is big boys. 525 amps. I need to parallel. Divide by 2, 263 amps. Take this one to 310.16, 75-degree column. I'm paralleling, guys. So I have 2 sets of 3 conductors each, 300 kcm RHW. 2 sets. Anybody has any issue with that? 2 sets. You guys are good with paralleling. Paralleling conductor is a nightmare sometimes. But on piece of paper, it's nothing. Go find double lugs on every phase and order things with double lugs. Everything has to be double lugged now, right? Where's my journeyman's here?
Yeah.
You can't put 2 cables under 1 lug, can you? Legally. Unless you
residential.
2 lugs under
Breakers.
one,
Two cables under one.
2 cables under 1 lug.
You cannot do it residential.
You can't do well. You can if the inspector is not watching.
Well, I mean, it was just, yeah, some, it's terminals are made for more than one.
Yep.
And they're not. Huh?
Breakers.
Breakers or not, you can't bring 2 in the 1 slot.
Okay.
Yes, they do.
Take him outside and give him a candy.
It's, no, you will get hammered on it.
But we all did it though. We have to admit. Oops.
But just to be right about that, it is not right.
Look at my angels here.
I never.
What? You're ahead of us? What's going on here? Controller size. Now, moving on. Am I going too fast? Sorry.
No, you're not.
No?
You're fine. Keep going.
Fine.
I've never seen you go this fast,
Okay, number 6. Number 6. Transformer size. So now we need to size the transformer. We need to size the transformer because we stuck that baby in between. We need to size the transformer separate. That's a new step.
Oh my God.
So we take 1.25 multiplied by the same thing, guys. 396 plus 24.2. That and what would that we just sized this one. What's the conductor size when we did them? We came up with 525. 525 amps. Right? That's step 1. We just put them in 2 steps here.
What is the code, the 125 again for continuous?
Continuous load for
Whatever.
motors 430 dot something. Continuous load. That's something.
Okay. Well, right on the test.
1.25, I'll get you. 1.25 times this. Okay. The next thing, guys, transformers are sized, Brad, in DeWalt number 1, and also they're sized in kVA. So the next step is to take the 525 times it by, what's the voltage, guys? 208 times 1.73, divide everything by 1,000. And if you guys did what I have done, I came up with 189 kVA. 189 kVA. Did you guys come up with something different?
That's what we came up with.
Came up with some? Okay. And then you 189 kVA, take it to D wall. What was D wall? 77? Is it 76 or 77?
7.7 for 3 phase.
77 for 3 phase. Thank you. What's the next standard? 225?
It says 225, but Spencer's got, in his book, he's got 200 kVA.
Spencer's is,
Spencer's book.
yeah, that Spencer's book has to be updated a little bit. 225. 2 kVA. 225 kVA.
I was with you. You're good.
Any question, guys, about this?
When did you get the 1.7?
Which one is it? That?
1.73?
It's 3 phase.
Oh,
It's a 3 phase.
I see. Okay.
Yeah, 3 phase. Any question, guys, about number 6? Was that number 6, number 5?
That was 6.
Yes.
That was 6.
Peter, number 6.
Because
Oh, yeah.
normally 1.7 we use it to have gallon.
Yeah.
Yeah.
So, sir, better.
Yeah. I was saying, it's there.
Okay, let's go to number 7. Can we go to number 7?
Please do.
Shall we?
DJ, should we go? I listen to you. Okay.
That's good.
Number 7. Number 7. Number 7. Overcurrent protection device for X for primary overcurrent protection device, or let's call it primary overcurrent protection device for transformer. The primary overcurrent protection device for the transformer. Kind of weird, a little bit how we do it. I want you guys to wake up if you're sleeping. And you have the rules in front of you. The first one, guys, the first thing you need to do is find locked rotor current for fire pump. And you guys remember it was an EF, the code letters for them? Is that what we said, EF? If you go to E, if I did that right, you go 4.99, multiply this by 150 times 1,000, divide this by 1.73 times 208. Remember, it's a 208 system. And you end up,
If it's the primary one, if it's 480.
we're not sizing anything yet. We're just finding the locked rotor current.
Oh, okay.
We're doing the locked rotor current. The locked rotor current is 208.0 amp. I'm finding the locked rotor current for the 2 pumps, guys, that I have. That's the first one. The second one, locked rotor current jockey pump. It's an F code letter, so that will give you a multiplier of 5.9. The upper limit, the worst scenario, 7.5 times 1,000. Divide everything by 1.73 times 208. This will get me 117 amp. Okay? So I found the locked rotor current for the 2 of them. Step number 3, my friends, we're going to add them. Add them up. 208.0 plus 117. When you add them up, DJ, you end up with 2197 amps. Auto calculation. This is the kind of a strange dealie. So we just add them up. Then look how they do it, guys. Now, Brad, this is where they shifted to the secondary. Look what they shifted. Remember, up to this point, guys, we're on the secondary part. This is how they shifted to the primary part. This is very interesting, guys. If you look at Am I the only one who's excited here, guys? Good grief. 2197 times 208 over 480. Do you see that what I did in red here? This will shift you from the secondary to the primary. And that will get you 952 amps. I shifted myself from the secondary to the primary. That's why I divided by the voltage ratio, guys. It shifted me from the secondary to the primary because that has to be on the primary. Brad said, well, Chad, why are you using 208? Because I was on the secondary first, then now I shifted with this ratio to the primary. And this is also on the sheet that you guys have.
So you multiply it by
Yep.
208 divided by 480.
208 divided by 480, yeah. Because the primary to secondary is 480, 208. The last step, my friends, and I really need to do it here, is to take the 952 amps, take this one to 240.6. What's my next standard overconduction device? That's 1,000. 1,000. That's it. How many steps? 1, 2, 3, 4, 5 steps. 5 steps. 5 steps. Any question, guys? So first you find the lock total current for the two pumps, add them up, then multiply them by the voltage ratio so you can shift yourself to the primary. Otherwise, look at that. Otherwise, look at how the amps, guys, went way down when I went to the secondary, from 2,197 to 952. It dropped because we moved to a higher voltage. The amp will drop.
Or in other words, if we take 2197 and then take the voltage, which is 480, and multiply conservatively the other numbers we're having, it will come 952. The number will be 952. In other words, I mean, if we take the process when we are finding the voltage, which is 480, will come the same amount. If we
Change this one to 480.
If we, for example, take that formula and change, instead of 208, 480, it will come the same thing, 952, right?
I have to prove that. I have to do the math on it.
Okay.
It might, because we're multiplying.
Yeah,
No, I don't
It's a change of.
think so, because we're adding here.
Oh, I see. Okay.
We're adding them.
Oh,
So no, it wouldn't. If you take it at 480 here, divide by 480, then you don't have to do the ratio. I don't think it works. Try it. Try if you can come up with the same answer. I don't think it works.
I will try.
I don't want you to do it, but
Yeah, okay.
any question, guys? I'm going to pull my calc book now, Mr. Irbab, and start working on calc here. Number 7, number 8. Now we're done. If you guys got this step, this is kind of the hardest one. The sheet that I have, you guys, everybody knows what VS over VP, V secondary over V primary, right? Anything on the sheet that I gave you that you don't understand what it means, please let me know. Okay, let's go to number 8. Number 8. Number 8, guys. XFR primary conductor. Primary conductor. The primary conductor, guys. The primary conductor. IP. The primary conductor. The step. We need to size the primary conductors. So remember, we have 225K transformer, KVA. Yes, 1.73. Thank you. It's on the primary. It's 480. You can use a table, no problem. You should come up with 271, Brad. No. So you can use a table. Yep. No problem. So you find the full load current of a transformer on the primary. You guys have done that many times with your Uncle Chad or Grandma Chad. And then from here, 271 amps, take it to 310.16 under 75-degree column. And that will get you 3 conductors, number 300 kcm. Most likely at this point, guys, you're outside, so you're using, let's just continue with RHW. Most likely you're using THHL, but let's continue with RHW conductor. Because it's a fire pump, very commonly used, RHW. Okay? Any question, my friends? Since number 9 is easy too, number 9, guys, auto transfer switch size. This is how we size it. You take the I primary, so already 271 amp, right? We already calculated. Take the 271 amps, grad DeWalt 312, DeWalt
What does that say?
3-12, sizing auto transfer switch. I primary, P. This is the same I, guys. I primary is the same I that we have here, 271. And we're going to size the auto transfer switch based on DeWalt 3-12. That will give me 400, right? 400 amp. 400 amp. So I have a 400 amp auto transfer switch. Now, if you guys go, we're using DeWalt. If you go and you find a manufacturer that make 300 amps, then can I use a 300 amp here? Disclaimer. Absolutely. Most likely, I'm using DeWalt just to get you some type of a standard.
Are we looking for sizes of disconnects? That's what
Yeah, I'm looking at the disconnect, Mr. Bear. I'm using the disconnect as my guide,
Okay.
but really, most likely you're going to find a 300 amp auto transfer switch. That's good. You go by the next standard, industry standard. Number 8 and number 9. Go to number 10. Number 10. Thank you. Number 10 and number 11. I heard that somebody say exactly the same. Number 10 and 11 are a piece of cake. And 12. Piece of cake. So let's go do that piece of cake. Can I move?
Yeah.
Anybody? Okay. So let's go to number 10. Number 10, my friend, as a conductor from the main. Conductor from main service, basically. This one is same as number 8, right? And what's the size? 3 conductors, number 300 kcm RHW. Done. Number 10, number 11. Conductors from Gen, same as number 8, right? And that will be the same thing. 3 conductors, number 300 kcm RHW. And I'm going fast on these guys because they're repeating themselves. Any question about these two? Piece of cake. The same as number 8. So when you guys do it, you just do number 8 and you write the same answer. No changes. The reason why I took them out, because they could be different. You could be feeding other things from the transformer bread. That transformer could be feeding other things. Then it would be completely different. Well, could be. Okay, can I move?
Mm. Yeah, you can move.
Thank you, Mr. Webb. You're the best buddy. Number 12, overcurrent protection device service side, from the service side. Okay, this one, guys, I say same as number 7. Thank you. And what did we come up with number 7? 1,000 M. Done. Let's go to number 13. No calculation. Number 12, same as number 7. Number 13 is slightly different. I don't know what I told you guys about number 13. Yep. Number 13 is slightly different. Over current protection device. This one is gen side, from the generator side. Did I confuse you if I use different language than I used here? I said overcurrent protection device from the backup source side. Would that make sense, Mr. Webb? The backup side, the gen side? Okay. This one, my friends, is step number is I primary. You go back to the I primary equal 71 amps. Step number 2, you take 1.25, multiply it by 271. That will get you a healthy 339 amps. I'll get you guys with the 1.25. And then you take the 339 amps, take it to 240.6, go up, and it's a 350 Brad Nelson, 350. And if anybody guys ask where the heck is Chad came up with this number here, this is coming from table 450.3b. Okay, like a transformer, a primary of a transformer. And if you guys read this, it has a note number 1. It tells you if you hit a non-standard 2. Did we say 2 or 3? 3 ways. Either you custom design yourself one, you go to the bar, drink and cry, or you go up. That's what that note number 1 will tell you. So for most of us, we'll go up. This is called cover your bottom type design. I can go down, by the way, but if I start the pump and the transformer trips, I will look so ugly that nobody will hire me again. That's why they go up, guys, in these. You can do anything you want when you're in the field. But the challenge is if it doesn't work.
Well, I think that they would probably just put a new size in there.
Yeah, I suppose, yeah.
Because they're going to test it before they.
Yeah.
Did they fire you? When
But you kind of look, we look kind of
did they,
not good.
Did they fire you when you burned that house?
Almost.
You burnt the house. Recording.
You're not recording?
Yeah. Oh, all my friends in Jerusalem are going to hear it. Yeah.
They weren't your friends anyway.
You're going to have an F. No.
What else is new?
Troublemaker, Chad.
I want to come back next year.
Any question, guys, before I put the homework in?
It's a fancy scale here.
He's into the science and learning. Why do you guys turn people off? The guys, okay, let's go to transformer. Okay, homework. Here's your homework, my friends. Homework number, Mr. Bab, that will be number 10.
Number 10, yeah.
Thank you. You're going to get 1 credit just for reminding you. Oops.
I appreciate it. We need that.
Oh no, Mr. Bab, you don't. You're just sharper than a tick. Homework number 10. Homework number 10. Well, guess what we're gonna do, guys? We're gonna make this baby 15 horsepower. We're gonna make this baby 200 horsepower. That's a big boy. And we're gonna spice it up for you guys. We're gonna make this system here, the we're gonna make this system 240 volt and 600 on the primary. We're going Canadian. And the code letter is C for this boy and D for this girl. Okay, everybody? So the transformer is 600 to 240, well-respected voltages on primary, secondary. The horsepower is 15 on the jockey pump, 2000 on the fire pump, C code letter for the jockey pump, D for the fire pump. And we're going to do the same steps. Does that guys give you an idea? In an hour and a half or so we spent, does that give you an idea how to size a fire pump system? Mr. Rebab, does it make sense?
Yeah.
Thank you. Keep assuring me. You're a good dude, Mr. Rebab. Okay. Yeah. That's all I have. Thank you guys for listening.